Is everyone ready to go?
Yep.
Okay. Speakers, any reason not to go now?
No.
Okay. All right. Well, let's go ahead and get started then. It's 11 a.m. Let me say thanks, everyone, for attending the fourth ECS and Cloud Feedback Virtual Symposium. My name is Andy Dessler. I hope everybody out there is doing well, staying healthy, wearing their masks. So just a few seminar notes. We're going to have three AGU style talks, 12-ish minutes. If you have questions, you can type them into the chat at any time, or you can raise your hand. There's a raise hand button if you go to the participants floating window, and we can unmute you. Your microphones, if I have this set correctly, which is always a 50-50 proposition, you should be muted and unable to unmute yourself. But we can unmute you if you raise your hand. We'll have a general Q&A for a few minutes after the last talk, for basically as long as everyone's willing to stick around. And lastly, probably most importantly, this works because people have been willing to volunteer to give talks. So email me or my co-organizer, Christy Procesescu, if you would like to give a talk. And with that, I will turn it over to Christy to introduce the first speaker.
Hi, everyone. Welcome to our seminar. Our first speaker is going to be Dan Lunt, a professor at the University of Bristol, and he's going to be talking about estimating ECS from past warm climates. Dan, take it away. I will give you a 10-minute warning.
So, yes, as you said, I'm going to be talking about estimating ECS from past warm climates, and in particular, the role of nonlinear feedback. So I'll start off with an example from 50 million years ago to set the scene, if you like, and then ask the question, is this a valid thing to do? Does it work, given what we know about the nature of feedbacks in ocean circulation? So the second part of this talk in particular is based on this paper last year by Alex Farnsworth, so I'd particularly like to acknowledge him, but also the other co-authors on this piece of work. So just by way of introduction, setting the scene in terms of timescale, here's a plot of the log of CO2 on the y-axis, so forcing due to CO2, and log time on the x-axis. So here we are today, about 400 ppm. We've got the extended RCP scenarios going off into the future. And then going back in time, we've got our best estimate of how CO2 has varied. And you can see, for example, about 1,000 ppm, perhaps an end of century sort of business as usual scenario. You have to go back about 50 million years to what we call the early Eocene, which is where this example comes from, to find a time period when CO2 was this high. And what else do we know about the state of the system at this time? Well, here's a figure of the geography of the planet. You can see it's quite different from today. There's no permanent ice anywhere. You've got India, for example, yet to crash into Eurasia. You've got Australasia near close to Antarctica. We also know sort of qualitatively some indicators about what the system was like. This is an artist's impression based on the fossil record of what Antarctica was like at the time. You can see some little penguins down here on the beach, but clearly a very different world, and a super warm world and super high CO2 world compared to the one we live in today. But what do we know quantitatively? If we're going to estimate ECS from this time period, we're going to need to know the temperature, obviously, and the CO2 pretty well. In terms of temperature proxies, there is a sort of a recent compilation of the locations of sea surface temperatures in the top plot and land air temperatures in the bottom plot. So you can get a feeling for sort of the distribution of temperatures that we have. If we look at this as a zonal mean, the grey band here shows the modern distribution of sea surface temperatures, and in the coloured points here, you have the estimates from this compilation for 50 million years ago. You can see warming in the tropical regions, but even more warming in the high and mid latitudes. So we're talking about a world with polar amplification, decrease in meridional temperature gradient, which is also reflected in the proxies we have for land air temperature as well. But you can get a feeling for the spatial distribution of this. They're relatively sparse. How do we go from this to a global mean? Well, this recent paper, talk about just in press as of yesterday, Ingalls et al. Applied multiple different methods to go from this sparse data set to a global mean. So, for example, taking the individual locations, collapsing them onto a zonal mean, and then using that to estimate the global mean, first of all, a simple approach. Also using model simulations of this time period as a sort of lookup table from local to global temperature. If you carry out multiple simulations at multiple CO2 concentrations, you can sort of interpolate and extrapolate from local temperature to global temperature. Then almost every temperature estimate you have becomes an estimate of global mean temperature that you can then average, and the associate uncertainties associated with that given the number of locations you have. Also, another method they applied, Gaussian process regression, where you have a prior that gives you the background distribution of temperature, and then when you come close to the proxy locations where they exist, then you sort of collapse towards those. And it also gives you an estimate of you can then average this global field to give you an estimate of global mean temperature. Or you can do even more simple things like fit a simple cosine latitude function that best fits the estimates of local temperature you have. And obviously with all these different methods, you can then apply them back to the modern climate, given an Eocene distribution of temperatures, and get a feeling for what the uncertainties in temperature that you have. And obviously the more sites you have, the tighter a constraint you can get on the global mean. And if you combine the uncertainty, the methodological uncertainties, if you like, along with the uncertainties in the estimates of temperature themselves from their calibration, you can end up with a distribution like this. We linearly pooled the results from the different methodologies. You end up with, in the blue line here, for the early Eocene climatic optimum 50 million years ago, so-called ECO. Here's our PDF of global mean temperature from that process. And you can see the error, the uncertainties are quite large, but we're talking about a big signal here. So it's a mean of about 27, 28 degrees, about 13 or 14 degrees warmer than pre-industrial climate. We also have estimates of CO2 in the atmosphere, indirect estimates from proxies of ocean pH effectively, which also have large uncertainties, but a big signal. And you can put these together and the associated uncertainties to give you an estimate of the ECS of the eco compared to the pre-industrial. And you can do things like take off the temperature change that we think is due to the reduced extent of the ice sheets to convert this to sort of an ECS from an Earth system sensitivity. So that's all very well. You get best estimates of around about, in this particular paper, got best estimates of 3.1 degrees C with an IPCC style sort of likely range from 1.8 to 4.4. So that's all very well, all quite standard. But an important question is this valid as an estimate of modern ECS? We're talking about the ECS here of a world that's very different from our own, as you can see here. And so a key question is, does this very different paleogeographic configuration of the continents and the lack of ice sheet affect the climate sensitivity? Does this eco-climate sensitivity have anything to say about our own future? So this is a question we were interested in, and so, as I'm a modeler, I went about this from a modeling point of view. So we carried out a number of simulations from 150 to 35 million years ago to answer sort of the general question about, in these warm climates, the role of paleogeography in ECS. We used the model HADCM3, which is a sort of CMIP3 class model, more like an EMIC really these days perhaps, but it's the sort of model that you need if you're going to carry out very long simulations, a large number of simulations for a very long time. So we actually carried out about 20 simulations through this period. Here's the paleogeography that we put in our model. You can see from 35 million years ago to 150 million, you go from a sort of continental configuration, not dissimilar from that of today, but to one of a sort of Pangean supercontinent when you get back to the earliest Cretaceous, as we have here. So we had a very simple experimental design. Here are simulations going through time. So all the following figures are all going to be back to front. They're sort of geology style figures where time goes from right to left, 150 million years ago here to 35 million years ago, which is when the Antarctic ice sheet began to form. And we carried out a set of simulations at 2 times CO2, 2 times pre-industrial CO2, another set at 4 times, and also had, as in agreement with sort of the theory of the evolution of the sun, a gradual increase in the solar so-called constant through time. So it's a really, quite a simple experimental design. You could look at these two forcings, CO2 and solar constant, and make a very simple sort of in the forcing and classical forcing and feedback framework. Choose a sensible feedback parameter, put in sensible values for the CO2 forcing and the solar forcing, and you'd end up you'll predict, if you weren't, before you carried out the GCM simulations, you might think it would look something like this. So a set of simulations that gradually warmth with the solar constant at the two different CO2 concentrations. And what would the ECS look like? Well, obviously that's just going to be a straight line through time. So that would end up with a constant ECS. But we've got another term here really, which is the paleogeographic, the forcing associated with the paleogeographic forcing. Now to first order, probably what we're looking at is an albedo forcing primarily related to the changing distribution of the continents, because as we go through time, the amount of ocean compared to land is changing because of sea level changes, flooding continental shelves at various points. We end up with quite a significant change in ocean area, and therefore a surface albedo forcing. Again, you can estimate this by putting in sensible numbers from the paleogeographies that we have, and sensible assumptions about planetary albedo and cloud cover to create a sort of geographic forcing. And if you do that, you end up with something like this. So this is reflecting not only the increasing solar constant, but also the changing amount of ocean area through time. And you predict the GCM to do something like this. And it turns out, well, actually, you'd have perhaps a constant ECS as well in this case. In terms of what the GCM actually does, well, these are that now, rather than this sort of simple forcing and feedback framework in orange, we've now got the actual GCM simulations in blue and red, and you can see they agree pretty well. They seem to capture the general signal that we see in the GCM. The correlation coefficient's about 0.6 or 0.7. But what about the climate sensitivity itself? Well, it turns out that the simple forcing and feedback framework is not a good predictor of that. The actual GCM predicts quite a range. If you actually look at the differences between the blue and red, a change from about 3.5 to about 5.5 degrees C in terms of climate sensitivity. So clearly something a bit unusual is going on. And the fact that this ECS itself looks a little bit like the absolute temperatures themselves at the 4 times CO2 tells us that maybe there's something nonlinear going on in terms of the feedback. So if we take the sort of the second order term from this simple forcing and feedback framework, sort of the Bloch-Johnson approach, add in an additional term, solve the resulting quadratic, we can again go back to our simple framework and make a prediction what it would look like now. And the absolute temperatures look pretty similar, but now we see this predicted evolution in ECS, which actually looks pretty similar to what the GCM is giving, apart from at a couple of interesting time periods that we have here that I'll talk about in a sec. So we can look in a bit more closely at this time evolving ECS. Here it is in a sort of Hoff-Muller style plot with time going along here and latitude.
10 minutes.
As you can see the polar amplification very clearly. But also if we look at this changing through time, this is a plot of the 4 times CO2 GCM simulations minus the 2 times. If you see just at these couple of interesting time periods in the middle of the animation, we have a couple of time periods where the 4 times CO2 simulation in parts of the Southern Ocean here and here, it's actually cooler than the 2 times CO2 runs. And those are the same 2 time periods where the prediction from the sort of nonlinear model is not agreeing well with that of the GCM. And if we look at these time periods in more detail, well, here's one of the time periods where the simple model does agree well with the GCM. Here's the change in temperature between 4 times and 2 times. Here's where the deep water formation is occurring, so mixed layer depth. You see it's very similar in the 2 times and 4 times runs. But if we go to the Salandian, which is this time period here, 50 odd million years ago, we see that there is this cooling that I said in the Southern Ocean when you go from 2 times to 4 times is actually associated with a big shift in the location of the deep water formation. It goes in this case from 2 times mainly forming in the Pacific sector of the Southern Ocean and partly in the Indian Ocean. Also, it goes to, that shuts down effectively, and you get deep water formation instead, partly in the North Atlantic and in the Atlantic sector of the Southern Ocean. Similarly, at the Maastrichtian here, where things are the opposite way around, the GCM at 4 times CO2 is warmer than we would expect. There is a flip the other way around, where we get a flip from towards at 4 times going to deep water formation in the Pacific Ocean. And what it appears like is that when you have these sorts of configurations with strong deep water formation in the Pacific sector of the Southern Ocean, we're getting a relatively warm climate in the GCM compared to other time periods. So then we can go back and answer the question which we wanted to ask right at the beginning, which is, how does this compare? What does the modern look like in the context of these warm past climates? So we carried out a similar pair of simulations under modern configuration shown here. And actually the ECS in the modern is one of the lowest that we have for any of the time periods that we have. And we can understand that actually through this forcing and feedback framework, in terms of the fact that the modern has a relatively low ocean area. There's a relatively large amount of land compared to some of these warm past time periods, and therefore the background global mean albedo is relatively high. It's also got the Antarctic ice sheet in there, and the low background CO2 all act to cool the background climate. And because the presence of the temperature dependent feedbacks, it means that the ECS is relatively low in the modern compared to these past warm climates. And so just to conclude, hopefully within my 12 minutes, I've shown that past warm climates have been used to characterize climate sensitivity. They're given one example. They're nice. It's a nice approach because it provides a largely independent constraint on ECS compared to some of our other more sort of traditional approaches, process-based or observational-based approaches. But it does have to be carried out with caution, in this case for warm past climates, which are probably the most appropriate for assessing ECS because their CO2 is going in the right direction. The signal is not dissimilar from that from a 4 times CO2 increase. But because some of these warm time periods have relatively low land area, and therefore relatively warm, high background CO2, and the lack of the reduced ice sheets coupled with the nonlinear nature of the feedbacks means that these past warm climates can have a relatively high sensitivity compared with modern. And that's even despite having this lower solar constant, which acts to slightly cool the climate. So I'll stop there and thank you for listening.
Thank you, Dan. That was a very interesting talk. Okay, so Q&A. We've got a couple of minutes. Either use the raise your hand function in the participants tab or type it up in the chat and I'll read out loud to make sure it's under recording.
I have a question, Dan. So you did these runs for different time periods with your model, and they were obviously, or I'm assuming, equilibrium runs. You're running it to equilibrium at 100 million years ago, 105 million years ago. How long did you run the model, and how did you sort of ensure that you were basically in equilibrium?
Yeah, so that's a good question, and the answer is, you have to run these simulations out a long time. This is we actually ran them out for about 10,000 years, and that's why we need we need to use a CMIP3 class model. This is the plot on the top left shows the time series of global mean temperature, global mean surface temperature. This is 1 times 10 to the 4, so 10,000 years over here. These are the set of 4 times CO2 simulations. This is the set of 2 times CO2 simulations. Probably we could have stopped about here. Maybe 8,000 years might have been sufficient. Maybe even 5,000. This is, if you're interested in ocean circulation changes, though, then probably you need to run them a bit longer. So this is at 3 kilometers depth. The evolution of deep ocean temperature shown here, and this is a Gregory plot. I mean, it's not a traditional Gregory plot, but this is, we're not sort of starting from a sort of an instantaneous forcing of CO2. This is a plot of the Each one of these dots is a single year representing the TOA energy imbalance, global mean temperature. And these block squares, these crosses that you might just about be able to see, are millennial averages. So 1,000-year average going down, and you can see it gradually approaching equilibrium. And maybe I also did this where I carried out, continued out the Gregory plots and estimated the temperature, and they're all very close. So the results wouldn't change very much if we calculate global mean in that way. But yeah, it's a good question. The answer to it is, well, I'm pretty confident now that we are at equilibrium, and you need multi-millennia to do this. So it's like a paleo long run MIP type simulation, I guess.
Okay, we got time for maybe one or two questions, and then Dan, maybe you can respond to some of them in the chat. So Natalie Burrows asks, any thoughts on the feedback mechanism associated with the Southern Hemisphere deep water formation changes?
Yeah, so that's a good question, and it's one that's it's very difficult to answer. It's one of the reasons why it's difficult to answer is because it's a very subtle. It's quite a subtle change. These flips that we get, they sort of flip backwards and forwards between. If I go back to this figure here. But anyway, the two time periods that I showed here are basically a sort of a flick backwards and forwards between the two ocean basins. Now, if you look at the ocean circulation, so in the supplementary information of the paper, we show the ocean circulation and deep water formation in all the simulations. But if we go to the earliest here, in the early Cretaceous, 150 million, basically all the deep water formations happening in the North Pacific. And that gradually slows down a little bit. In these simulations during the sort of mid-Cretaceous, there's actually, for some of them, there's very little deep water formation anywhere. And then it gradually begins to form in the South Pacific here, and then flips gradually into the North Atlantic and other sectors of the Antarctic later on. But the mechanism, I think, is largely paleogeographically driven, and the reason, and I can't answer it exactly, but for example, the North Pacific ocean circulation, the very strong North Pacific ocean circulation that we get at the beginning of the earliest Cretaceous is almost certainly associated with the fact that the sort of continental arc here that joins North America and the Eurasian continent is much further north at that point. So literally you can get much colder waters in that North Pacific sinking, but the reason for the flips in the Southern Ocean, I'm not so sure about.
Cool. Okay, I think we have to move on. We can come back to some of these questions at the Q&A at the end, but in the interest of time, we should move on to our second talk. And our second speaker is going to be Isabel McCoy. She just finished her PhD at University of Washington and is starting a postdoc at University of Miami. I think I have that right.
Yes, let's see. Can you see my screen?
Yeah, you can see your screen.
Okay, excellent. Yes, thank you for the introduction and the invitation to share some of our work today. So today I wanted to talk about a recent paper that my co-authors and I just published, looking at how we can use the hemispheric contrast and satellite-derived cloud microphysical properties to constrain aerosol forcing. So as sort of the bit of background on this, right? So we expect that aerosol radiative forcing is a leading uncertainty in inferring climate sensitivity from the observational record. And this is nicely summarized in this figure from Andre and co-authors in 2005. So essentially, the idea behind this is, as I'm sure many of you are aware, is that we can figure out where we are on this curve if we know how much present-day aerosol forcing there is. So if we're further to the right, we have more aerosol cooling, and we'll have a higher climate sensitivity. So we really want to know, as Dan nicely presented earlier, how we've changed from the pre-industrial state to our present day. So in particular, how have we gone from those sort of pristine natural emissions to our current anthropogenic and polluted environment. So aerosol radiative forcing can be broken into two parts. So aerosol radiation interactions, or ARI, and aerosol cloud interactions, or ACI. And as it turns out, liquid cloud ACI strongly contributes to the uncertainty in aerosol radiative forcing. This is from a paper by Belwan and co-authors in 2019. And so this really encourages us to look at aerosol cloud interactions and try to understand the uncertainty around those, so we have a better idea about the overall aerosol radiative forcing and a better estimate of climate sensitivity. And in particular, in this talk, we'll be focusing on radiative forcing, so RF-ACI, which used to be known as the cloud albedo effect. And we won't really talk about adjustments that much, so we'll mention it a little bit. So radiative forcing, or RF-ACI, from aerosol cloud interactions, as many of you might remember, it is essentially the idea of having a cloud that you then add aerosol to, but you keep everything else about the cloud the same. So it's all macrophysically identical. And the end cloud that you get has more droplets, right, because you've added more cloud condensation nuclei to it. But each of those droplets is smaller because you've had to distribute the liquid water in the original cloud around those new aerosols. And so this results in a brighter cloud overall because more of those droplets are smaller, and so that's brighter. And so we can actually measure this as cloud droplet number concentration, or ND. So we can have sort of a direct estimate of that. And so we can try to understand this as sort of the framework of RF-ACI, right, where you've had this pristine pre-industrial state, you've added all these anthropogenic aerosols, and then you get these brighter clouds at the end. So that's kind of the premise of this whole thing. So as it turns out, we actually can measure cloud droplet number concentration, or ND, by satellites. And there's been a lot of work looking at this. I've listed some of the papers, so this isn't extensive by any means at the bottom here. But we have a pretty good estimate of this ND quantity from satellites. In particular, I'll be working with this MODIS satellite. And this is from a paper by Daniel McCoy in 2018. And you'll notice a couple of things right away from this plot, right? So we kind of expect, right, northern hemisphere, it has these anthropogenic polluted environments. And you can see off of these continents that you have these sort of continental outflows where you have pretty high droplet number concentrations. And then in the southern hemisphere, you also expect to have these, right, pristine environments where you have natural emissions, right? You don't have that many continents there, so you just don't have a lot of those anthropogenic off-sourcing there. And you kind of expect it to be overall maybe a little bit lower, as you can see, since there's more red up here. But what was really interesting to us is that if you kind of zoom in on the Southern Ocean area, we actually do find that there's droplet number concentrations that are pretty high near these continents in particular, though maybe not across kind of all the Southern Ocean in general. And we also see something else that's really interesting, which is that there's a really big seasonal cycle. And so because we have kind of more confidence in the satellite product, we kind of trust that this is showing us what's really happening in the real world here, and that it's telling us about what the aerosol is that's driving these droplet number concentrations. And in particular, because you have these summertime peak droplet number concentrations compared to the winter, right? The satellite doesn't get all of that glow, but you get enough to get this kind of cycle. You see that those aerosols are likely biological, right? So they're likely associated with those kind of big seasonal cycles that you see in that region associated with phytoplankton. So that's quite interesting to us, and we'll come back to this point as we kind of go forward. But overall, I just wanted to kind of say that we have pretty good confidence in this droplet number concentration product from MODIS. And so now that we have this present day droplet number concentration, can we use that to constrain RF-ACI? So again, we run into the issue of we don't know what was happening in the pre-industrial, but luckily there's been a lot of work looking at whether we can use any of our present day environments as this kind of pre-industrial equivalent. So there's a really nice paper by Hamilton and co-authors in 2014 that found that southern hemisphere oceans are our closest pre-industrial environment in the present day. So we can kind of say that these are sort of equivalent, and then that lets us form this kind of simple cartoon that we can think about this problem in. So the blue line here is for the pre-industrial, and you can see that it's pretty flat. So it's a little bit higher in the northern hemisphere, just because you have continents there and you have some amount of aerosols that are naturally emitted from continents. But it's quite flat in comparison to this present day curve that we expect, right? So in the present day, you have this huge droplet number concentration in the northern hemisphere associated with all those anthropogenic emissions. At least that's kind of what we expect. And in the southern hemisphere, again, it's kind of flat, right? This is the Hamilton idea. So maybe we can say that the difference between the northern hemisphere present day and the southern hemisphere present day is equivalent to the difference between the present day and the pre-industrial. And that difference is what we can use to try to constrain this RF-ACI. So to do this, we looked at a number of different data sets. So the first is this observation product from the MODIS Aqua satellite that I was showing you. And then we have kind of two groups of models. So the first group of models is made up of these Aerocom phase 2 indirect 3 and these sensitivity studies in HEGM3 GA6 to 7.1 development runs, those done by Jane McCoy. And that's telling you about kind of uncertainty between models, right? Because you have a bunch of different ones. And then the second grouping of models is from this perturbed parameter ensemble, or PPE, from the HEGM GA4 UKCA. And this was run by Leighton Regehr and Ken Carswell at the University of Leeds. And the idea behind this is that you have 26 aerosol process emission and deposition parameters that you can simultaneously perturb. And that lets you kind of explore the space within this model and look at kind of the uncertainty within that single model. Now, in order to do statistics on this, you need to create an emulated surface. And so this emulation of the PPM members was done by Duncan Watson-Paris at the University of Oxford following his 2019 paper. Okay, so we have these data sets, and then we can see if this kind of cartoon model works with these models, right? So the plots that I'm showing you, and we'll come back to these plots in a little bit, but just the takeaway that I want you to have right now is that you see that there are these zonal maps of the present day from the model and the pre-industrial in blue here. And I've also plotted this MODIS observations on top of it. And this is for December, January, February, and June, July, August. And so if you look within these mid-latitude bands in particular, you can see that this cartoon model actually does pretty well, right? So in the northern hemisphere, you have a separation between the pre-industrial and the present day. And in the southern hemisphere, you kind of have a collapse of both of those simulations. Okay, so that seems kind of good enough to be going forward with. So can we say this? Does the hemispheric contrast contain information about this change in droplet number concentration from the pre-industrial? So the simple answer to this is yes, but let me kind of walk you through it a little bit. So on the x-axis here, we have the hemispheric contrast between droplet number concentration in the northern hemisphere and southern hemisphere. And on the y-axis is the difference between the present day and the pre-industrial droplet number concentration. Now there's a lot that's on this plot. The triangles are telling you about those individual models. So the orange is telling you about the Aerocom model. The kind of bluey greens are from the HEGM development runs. The pluses here are the individual PPE members. And then this kind of blue smear is that smooth emulated surface that's been fit to them. And because we have the emulation, we can then fit this best fit line and this 95% prediction interval. Now, these again are all from the models, but we also have the observations here, right? So this is this gray bar. And we find that at 95% confidence, this difference between the hemispheres from MODIS is between about 32 and 37 number per cc. And you'll notice that there are some of these models that overlap, and in fact, these Aerocom models fall pretty well in the best fit, so that's exciting. And because we have this overlap here, we can use these observations to constrain, and in particular, constrain these PPE. And so this MODIS constrained range for the change between present day and pre-industrial is between about 8 and 24 number per cc at 95% confidence. Okay, so the big thing that I want you to take away from this is just that there's a relationship here, right? So there's a slope, and you can say that this hemispheric contrast has a relationship with this pre-industrial present day difference. And we really want to be able to use that then to look at RF-ACI. So I've now swapped out this y-axis for RF-ACI. And you'll notice that we've lost some of these models. And this is because the Aerocom and the HEGM development runs also include adjustments. So you remember that the overall ACI includes both RF-ACI and adjustments. And we just want to look at RF-ACI, and that actually happens to be for the PPE. It only includes RF-ACI. So great. So we can apply the same methodology again and use our MODIS observations to constrain this range. So at 95% confidence, we find that the PPE RF-ACI range is between about -1.2 and -0.6 watts per meter squared. And so this is actually kind of exciting for us because it's comparable to the recent synthesis range that was developed by Belwan and co-authors using GCMs and remote sensing in a completely different methodology, right? So they find between about -1.2 and -. So Thank you. So that is encouraging in the sense that it seems like there's information in this hemispheric contrast that we can use, and it does a pretty effective job at constraining this RFACI quantity. Now, one of the questions that you might have going through this is that why are there so many models and PPE members that are outside of this observed range of droplet number concentration between the northern hemisphere and the southern hemisphere? And some of this can maybe be explained by looking back at these zonal maps. So we are just using the mid-latitude bands here, but even within those kind of constraints, we see that there's some kind of big disagreements between the models and the observations. So in particular, we can see that the northern hemisphere model droplet number concentration tends to be too high. And in the summertime mid-latitude droplet number concentrations from the model, those tend to be too low. And in particular, we really see this in the Southern Ocean. And so I've bolded this because I think this is a really important point, which is that pristine environments are really quite complicated, but they're very important to get right in these models. So this diagram is kind of a lot to go through at the last moment here. But so this is looking at the Southern Ocean. And you can see that there's a lot of different stuff going into this. And really the only thing I want you to take away from this is that droplet number concentration is a balance of both sources of aerosol and sinks of aerosol. And you can actually see this if you look at the zonal map, right? So you have this little divot here, and that's associated with precipitation removal in the storm track. But you also see that the model is really not able to get this high droplet number concentration near Antarctica. And that's telling you that the aerosol sources, because there aren't really a lot of sinks there, but that the aerosol sources aren't being appropriately represented in the models there. And that's kind of interfering with our ability to be able to produce the accurate droplet number concentration in the real world in these models. So let me just finish here briefly with these couple of last points. So hopefully I've motivated that cloud droplet number concentration helps us to understand cloud aerosol interactions and can be used to test models, that the southern hemisphere droplet number concentration is a rough proxy for pre-industrial droplet number concentration, and that southern hemisphere droplet number concentrations in GCMs is too low. And so that has an implication that the pre-industrial may have had a higher droplet number concentration than predicted by models, and that we aren't capturing those pristine environments sufficiently. And with this methodology, we've actually been able to produce an RFACI range that is similar to these other synthesis range, which is quite encouraging. So if you're interested in kind of more information on this, I'll direct you to our paper, and you're also welcome to email me with any questions. And with that, thank you for your attention.
Thank you so much. That was a great talk. So again, type your question in the chat or raise your hand in the participants tab. So we got a question from Robert. Isabel, what in situ validation for the drop number concentrations exist? The seasonal contrast around Antarctica is interesting, but retrieval near poles in winter might be quite biased given low sun angles.
Yeah, so that's a great question. Let me see if I realize I stopped sharing my screen. Yeah, so there's a lot of droplet number concentration kind of validation that people have looked at for other parts of the world. In the Southern Ocean, at least in this paper, we tried to look at some other sources because there aren't a lot of measurements right near Antarctica. And so this figure, I don't know if you can see it, is looking at kind of a variety of aerosol sources in that region to see if your sort of aerosol pattern and seasonality makes sense with the droplet number concentration. And so that's what this plot is showing you on the top here. And it's looking at McMurdo Station and this King Sejong Station. And then additionally, you can look at both the Orcus and off-cap flights that happened in that area. And then there's a more recent paper by Li-Tai Kang at the University of Washington that I think is in review right now that used Socrates observations. And so that would be about here, and found that there's a good match between the observed droplet number concentration and the in situ droplet number concentrations. So, sorry, the MODIS droplet number concentrations and the in situ droplet number concentrations.
I don't know if, Christy, if you saw the message from Steve Klein. Very nice study. How were cloud droplet numbers assessed in GCMs? Are there any observational issues in comparing GCMs to observations?
Right. Thank you, Steve. So yeah, so we're looking at droplet number concentrations produced by the models from variety of sources, and then so it's divided by cloud fraction, so you're not having clear sky in there, and then it's also weighted for liquid water path, so you're getting sort of the juiciest part of the cloud, which is kind of the best comparison with the observations. I don't know if that answers the question completely.
Can I have a follow-up on that? When you say GCMs from various sources, what GCMs are you talking about when you talk about all GCMs? For people running GCMs, it matters which ones you're talking about.
Okay, fair enough. Yeah, so sorry, I was talking about this slide. So we have, so unfortunately, droplet number concentration isn't produced by all models, and so we're sort of constrained to looking at these AeroCom phase 2 models. So this is indirect 3, so it's the CMIP 5 models, but they'll do this again for the CMIP 6 models, and then these various sensitivity studies from the HEGM, and then we also have it from the PPE from the HEGM GA4 UKCA.
Okay, thank you. I think in the interest of time, we should move on to our last presentation, and we can come back at the end for some Q&A if there's time. So our last presenter is Dennis Hartmann. He is a professor of atmospheric science at the University of Washington.
Thanks very much. How are we doing on seeing the screen?
Yeah, that looks good.
Okay, so I want to talk about some simple experiments to study the thermodynamic factors that control tropical sea surface temperature contrast. My co-workers are listed here, and there is a paper in revision that you can find online if you're interested. Oops. Here we go. So motivation is, I think in previous talks you've heard about the tropical sea surface temperature contrast being central to pattern sensitivity, and also that the maximum tropical sea surface temperature has global effects on sensitivity and climate impacts. So what are the key thermodynamic mechanisms ignoring ocean heat transport? Well, there's this idea of the convective super greenhouse effect, that in the convective regions of the tropics, there's higher moisture in the atmosphere, and therefore the greenhouse effect is amplified. We have the idea that there's a low cloud response to stability increases, either because the climate is warming up or because the temperature contrast is increasing between the convective and the non-convective regions. We have a high cloud response to sea surface temperature. In observations, Ramanath and Collins said, well, gee whiz, the reflectivity of the clouds increases so fast that we think the tropical sea surface temperature can't exceed a particular value. So that's constraining the sea surface temperature in the convective region. And then finally, there's the slowing circulation because of the warming and the greater stability due to the moist adiabatic lapse rate that slows down the circulation in the tropics. So what's a good modeling methodology to investigate the interaction between deep convection, the large scale circulation, and low clouds? Many people would turn to a convection resolving model with like 1 kilometer resolution. Has the advantage of not requiring convective parameterization, but the resolution is still not good enough to resolve boundary layer clouds or turbulence within anvil clouds in the tropics. And generally speaking, these models are not tuned to observations, and they're not converged in the sense that if you present different models with the same external conditions, they produce the same answer. Also, from my perspective, a big disadvantage that they're very expensive to run in a domain large enough to represent both the cloud scale and the large scale interactions. So we then turn to a general circulation model, which has a boundary layer parameterization. They are tuned to observations and they're computationally efficient enough for these global scale interactions I'd like to investigate. So to be practical, let's see if we can gain any robust physical insights using a global GCM in a simplified framework. So that particular GCM we're going to use is going to be run under the specific conditions that there's no rotation, uniform insulation, and a slab ocean, so no ocean heat transports. We're using the AM 2.1 GCM with 32 levels. The one that was used for CMIP5 had 24. We've left the resolution of the boundary layer similar and just increased the resolution in the upper troposphere and stratosphere because we're going to do some kind of extreme warming experiments. Now we're going to use a tropical ozone profile specified as a function of pressure since we don't have a photochemical scheme in the model. And we're going to vary the temperature by varying the insulation, which is because things are dominated by the thermodynamic response of water vapor. You wouldn't get wildly different results in equilibrium if you warmed it up by using CO2. So a sea-surface temperature contrast naturally develops with a warm convective region and a cooler subsiding region. The model oscillates, and similar behavior has been observed in the ECHAM, NCAR, and LMD models by the papers quoted there. So if you look at a typical sea surface temperature and surface wind distribution, in this particular case, you're getting one cold pool and one giant warm pool. And the four panels are illustrating the oscillation that occurs within the model. Upper left is the growing sea surface temperature contrast. Upper right is the high sea surface temperature contrast. And then there's a decaying sea surface temperature contrast. And then finally, the case with the minimum sea surface temperature contrast. So let me give you the conclusions for the mean state variations, and then I'll go on to try to show them to you. All right, so as the climate warms, the greenhouse effect in the region of rising motion increases faster than the subsiding region. That seems to dominate the response of the sea surface temperature contrast with increases in sea surface temperature contrast. And cloud effects work to reduce the sea surface temperature contrast, including the low cloud response in the subsiding region. And one of the robust results that came out of this is that the radiative cooling rate becomes more top-heavy with warming while staying at about the same temperature. Because we have a theoretical explanation for this, which I'm going to give you. So this is the one robust result, which I don't think depends upon any of the parameterizations in the model. And you can extend that result to say, well, this more top-heavy cooling rate requires a more top-heavy convective heating rate, and therefore we should expect to get more anvil cloud ice in a warmer climate. And we have some other experiments underway to try to test whether this is actually the mechanism for producing the increased ice that we see in these warmer climates. So just to look at a plot of the sea surface temperature difference as a function of the mean sea surface temperature, the blue dots are the difference between the top 20% and the lowest 20% of sea surface temperature. And you can see that if you start from a temperature similar to the current climate, it increases up until about 309 Kelvin, and then it declines again. And the blue lines are the difference between the rising region and the subsiding region. You can see that that also increases, although the contrast is smaller. Now, the main reason for that, as I said, is because the greenhouse effect increases more rapidly in the rising region than in the subsiding region. So the red dots are the greenhouse effect in the region of rising motion. You can see that it increases rapidly over the range of temperatures going from the current tropics to the future climates. And most of that is coming from the clear sky. The difference between these two lines is the long wave cloud radiative effect, which remains relatively constant as you warm the climate. And that's because the emission temperature from the clear atmosphere and the emission temperature from the top of the clouds tends to remain constant as you warm the climate. In the subsiding region, the greenhouse effect has almost no response to the sea surface temperature. So the top of the atmosphere, outgoing long wave radiation is increasing at about the same rate as the surface emission. And that's partly because of the lower relative humidity in the subsiding region, but also because the temperature difference between the rising region and the subsiding region is increasing. So the atmospheric temperature in the subsiding region is tied to the atmospheric temperature in the rising region. And that gives you a very, very weak greenhouse effect response, similar to what Pierre Humbert talked about in his 1995 paper. And in consequence of that, the sensitivity of the model between current and future is very, very low. It takes about 4 watts per meter squared to increase the temperature by 1 Kelvin, and that's because the sensitivity of the outgoing long wave radiation to surface temperature in the global mean is about 4 watts per meter squared per Kelvin. So a very weak greenhouse feedback. The clouds, on the other hand, are doing different things. The red dots tell you sorry about that, the net cloud radiative effect in the rising motion. The blue dots are the net cloud radiative effect in the subsiding region. And you can see that it's becoming more negative here, but you have to remember that we're warming up the climate by increasing the insolation. So let's have a look at what happens if you normalize the net cloud radiative effect by the insolation. And then you can see that in the subsiding region, the blue lines here, the effective enhancement of the albedo by the clouds in the subsiding region is actually declining. So the clouds are becoming less reflective as you warm things up, whereas in the region of rising motion, they're becoming more reflective as you warm things up. If you look a little bit more carefully at the low cloud response to warming, on the left, as a function of pressure, is the liquid water content. You can see that it increases a fair amount with warming, but the effect of this on the albedo is pretty much canceled out by the increased absorption of solar radiation by water vapor in the warmer climate. And the cloud fraction in the subsiding region is staying roughly constant. This is a feature, of course, of the low cloud parameterization in this model. The estimated inversion strength and the lower tropospheric stability are increasing pretty dramatically as you warm the climate, but these effects are apparently offset by the thermodynamic effect of the warming in this particular model. Let's now turn to the long wave cooling becoming more top heavy with warming. On the left is the long wave cooling in the downward region as a function of pressure. And you can see that that's increasing substantially in the upper part of the model as the climate warms, but not so much lower down. So the cooling rate is becoming more top heavy with warming. And the same thing happens in the upward region. And in the upward region, you're also seeing that as you warm it up, it's becoming more uncoupled. And that's part of the reason why the sea surface temperature contrast declines as the temperature increases further. If you translate, yes, 10 minutes, good. So if you translate radiative cooling into convective heating, you can see a similar sort of behavior. The convective heating has to balance the long wave cooling. And if you look at that on the right-hand side in temperature coordinates, you can see that the required amount of convective heating is increasing in response to the required balancing of the radiative cooling rate. So there's the convective heating rate as a function of temperature for those warming experiments. And this is the ice content, which tends to follow it very, very closely. And we can explain this by considering the cooling to space approximation. And it has an emission part, which only depends upon temperature, and a transmission part, which has a pressure dependence. So as it warms up and the emission moves to higher in the atmosphere, the transmission to space becomes easier, and that's what causes the cooling rate to increase as you warm the surface climate. And you can make the argument that this argument should also apply to clouds, which tend to remain at the same temperature. As they move up, their emission to space will cause more effective cooling because of this reduced transmission term. And you can test this in a one-dimensional model and get exactly this result in a simple framework using a moist adiabatic adjustment, a realistic adaptive relative humidity, and fixed tropical ozone. So it's a very basic radiative effect. There are some conclusions from the oscillations, which I didn't have time to talk about, so let's go to my main conclusion. So the radiative cooling rate in clear sky becomes more top-heavy with warming. This suggests an alternative, and I would say more robust explanation for increasing cloud ice in a warmer climate. More required convective heating means more ice. This is an alternative to what I consider to be the alternative idea, which is that if you have more ice coming up in a warmer climate and a fixed precipitation fraction, then that means more ice in a warmer climate. But before, you saw that the anvil clouds are always existing at the same temperature. So why would the amount of moisture coming up from the surface affect that as robustly as the increasing radiative cooling rate where the ice is actually occurring? I list here also a conclusion from the looking at the oscillations in the model, which reveals a very strong role of transport in controlling the sea surface temperature contrast. If you increase the sea surface temperature contrast, the transport out of the convective region increases, and that has a direct impact on the surface evaporation and the cloud shading. Of course, the caveats are, will rotation or ocean heat transport nullify these basic thermodynamic constraints? I think not in their totality. I thank you for your attention.
Thank you, Dennis. Anybody have any questions for Dennis? Okay, we got a question. Nice talk. Does the ozone parametrization take account of the change in tropopause pressure in the warmer simulations? I think that has been a problem in some GCM simulations with very warm climates.
Indeed, the ozone is fixed at a constant pressure, and so we do not adjust the ozone as we warm things up, and that is a constraint on how things behave. We have done some no ozone experiments, which in which you can see that the same things develop. The basic conclusions are unchanged. Part of the reason for that is once the water vapor gets up into the region where you have ozone, it dominates the thermodynamics. Even though the ozone is there, the effect of the water vapor is much more powerful. So it doesn't have a huge impact on the behavior, although it does change the mean temperature of the clouds and a few other things in an important way. Thank you.
Cool, thanks. Question from Nick Lutzko. If the radiative cooling rates become more top-heavy, do the descent profiles also become more top-heavy? Would this act to weaken the estimated inversion strength?
That's an interesting question. Of course, the downward motion also changes. One interesting thing about the vertical velocity in this model is that it has a, maybe I can actually show that. It has kind of a square distribution. If you can see here, and this part down here is tied to the surface heating and is fixed in pressure. This part up here is tied to the radiative cooling and maintains a constant temperature. I don't think the fact that the subsiding motion increases where there are not clouds and not vertical motion has much effect on the ice, because the ice exists almost entirely in the region of mean upward motion in the convective region.
Okay, a question from Angie. Dennis, very interesting talk. When you mention a fixed precipitation fraction, do you mean the area fraction? Things like my work with you and some work now showing a decrease in ITCZ width points towards a potential decrease in the area of precipitation. Can you talk about what implication you think that might have?
Okay, in these simulations, the subsiding fraction increases a little bit as you warm the climate, and so the convective region does shrink. When I was talking about precipitation efficiency, which is a parameter that people tend to look at in cloud resolving models, etc. I'm not sure how to answer the rest of your question. The other factor is that the vertical velocity does increase in the upward region and decrease in the downward region as you change things, and the precipitation rate does increase more or less following the net radiative cooling, which is increasing because it's becoming more top heavy and extending upward. I'm not sure I answered your question, Angie.
Okay, well, we can stick around for a couple more Q&As if people want to, but to be mindful of everybody's time, I want to thank everybody, especially thank our speakers for agreeing to give talks or for volunteering to give talks, and thanks everybody for participating. We had a good showing despite school starting for a lot of people, so if this interest persists, we're probably going to try to keep this seminar series going as the school year starts. I don't know if Andy wants to say anything. If not, we can go back to the Q&A.
Yeah, no, just remind people, if you're interested in giving a talk, email Christy or myself, and we'll stick around and continue to answer questions as long as there's interest.
Okay, so let's go back to the Q&A. Torsten has a question. Did you find the oscillations depend on the temperature? In ECM, we found it to only start with more CO2.
So the oscillations are strong for temperatures from the sea surface temperature of the current climate to about 309 Kelvin, at which point they decline. And the reason they decline is because the sea surface temperature contrast is declining. And that happens basically because of clear sky radiative constraints. The oscillations also get faster and weaker as you warm things up, which I think is reflective of stronger thermodynamic feedbacks. So the system is becoming stiffer, and the resistive forces to the sea surface temperature contrast are getting stronger. So it oscillates a bit faster, and then it disappears around 310 Kelvin or so.
Thanks, Dennis. That's funny because it behaves completely the opposite way in ECM. So that would be interesting to compare.
Yes.
Anyway, thank you. Thanks for a nice talk.
Cool. Gavin asks, are biases in stratospheric dynamics, i.e. the strength of the Brewer-Dobson circulation, tropical upwelling, QBO, going to impact this result?
I don't know. I think in one-dimensional simulations, we've found that the tropopause temperature, which is what the Brewer-Dobson circulation controls, is not a key factor in determining where the radiative cooling occurs, at least for the current climate. I don't know how that would change in a warmer climate, since we don't actually simulate a Brewer-Dobson circulation at all in these tropical world framework computations.
Cool. Well, if you have any other questions for the other speakers, those are also welcome. I have more of I'm going to use organizer privilege and make more of a comment and a question on Isabel's talk. So Isabel, you compare your results with the Bellon et al. Range, but I think that range contains both process information and information from the evolution of the global energy budget, and their process constraints are a lot weaker on the low end. Most of the low end constraints comes from energy budget. So I think your paper presents a much tighter constraint actually than that big assessment, at least from the process side.
Yeah, so yeah, it's certainly our numbers are more constrained. But I guess as part of that, we're also only looking at a single observation. And so I think there's a little bit of hesitation to kind of that sometimes can produce overly narrow constraints. And so I think we didn't want to be put a lot of emphasis on that in some ways. And it is just looking at the process portion. So it would be interesting, I guess, to compare to the more like process-oriented number in the Bell-1 paper instead of the total.
I see. Thanks. Dennis has a question for you. Isabel, how can you trust the models on this when they are so different on the current climate?
Oh yes, this was the same question I had in my defense from Dennis, I think. So yeah, so the PP models members that we're looking at, you do have more overlap than, so the zonal maps that I'm showing are for the AERCOM and the HADGEM models. If you look at the PP model members, it has some capability to have higher droplet number concentrations in the Southern Ocean, but it still doesn't get the really high droplet number near Antarctica. So it has a little bit of overlap, but so I think you can constrain it, but yeah, it is worrisome that the models are so far outside of what we actually see in the real world, which is sort of the emphasis, I guess, for the continuing to look at pristine environments and understanding aerosol cloud interaction like processes and having those appropriately parameterized in models. Is that a better answer to the question, Dennis?
It's a lovely answer. Thank you.
Sure.
Okay, I think one more question from Manoj. For Isabel, I think CMIP6 GCMs such as HADGM GA4 have much smaller surface shortwave biases than before, but it looks like there's still a bias in aerosol amount near the Antarctic coast. Does this imply another counteracting bias?
Oh, interesting. Okay, that's an interesting point. So I'm not as familiar with GA4 and what exactly has changed in it. I know that like CAM6, they changed their amount of supercooled liquid cloud, but you still have pretty large biases there. So I think there are maybe improvements that you're having in one aspect. We also did some work associated with a field campaign in the Southern Ocean area that looked at comparing with CAM6, and there are competing biases, we think, that are affecting the droplet number concentration. So it seems like it may be a combination of sources and sinks not being in balance correctly to get ND, which I guess is the sort of use of getting, of looking at ND, because it's sort of the summary. I don't know if that answers your question completely.
Okay, one question for Dennis. Dennis, do we expect the form of ice to change, Anvil versus Cirrus?
That's a question I'm extremely interested in. I think the anvil turns into cirrus. It's part of the same life cycle. I don't know the answer to that question. I don't think the models do a very good job of simulating the basic physics of anvils. And in the cloud resolving models, there's a lot of sensitivity to how you do the microphysics. So I think how the anvils and the associated thin cirrus change in a warming climate should be a hot topic of research right now.
Okay, let's take one last question from Yoko. I think this is for Dennis. So lapse rate feedback contributes to more negative feedback, but the top-heavy cooling contributes to less efficient radiative cooling. Is my understanding right? What kind of evaluation do you think will help contain the radiative cooling feedback in climate models?
Okay, so the top heaviness is how the atmosphere, let's be generous here and say the atmosphere actually is able to cool and provide a negative feedback. If you did not have that increasing cooling in the upper atmosphere with warming, the climate would be super sensitive. So that's kind of a key mechanism for the for the atmosphere to be cool. Most of the cooling to space comes from the atmosphere. And as the moisture increases and the lapse rate decreases, you would think that it would be really hard to emit to space, but how it does that, it keeps emitting from the same temperature and through an atmosphere that's getting thinner. So that's actually how it remains stable. Maybe I misunderstood the question, but that's how I see it.
Okay, thank you. So I think with that, this is a good time to end. Let's thank the speakers again, and we'll see you next time. Bye, everyone.
Bye.
Thanks, everybody.
Thank you.
Bye-bye.